When people first hear about an AI model being built and deployed, it's easy to imagine it like a normal app that gets installed once and then just runs. That mental picture is comfortable, but it's also risky because models behave more like living systems that change in usefulness and safety as their environment changes. A lifecycle view is the simple idea that a model has stages, and each stage has different goals, different mistakes, and different security exposures. The faster you learn to think in lifecycle states, the faster you can make sense of scenario questions that ask what to do next, what went wrong, or what control matters most. You don't need to be an engineer to think this way, because defenders already do it with other systems, like software releases and incident response. The difference here is that data and behavior are part of the system, not just code, so the lifecycle needs to account for both. By the end of this manuscript, you should be able to explain the four big states clearly: training, tuning, serving, and retirement, and you should also be able to describe what it means to exit each state safely. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A helpful way to ground the life cycle is to remember that a model is not just a file that predicts something, because the model is shaped by data, objectives, and evaluation choices that can lock in risk. In the training state, the system is learning from examples, and that immediately raises questions about what data was used, who controlled it, and whether it contained sensitive or poison content. In the tuning state, people adjust the model or its settings to improve performance, which can accidentally create overfitting, regressions, or new unsafe behaviors. In the serving state, the model is exposed to real inputs from users, systems, or attackers, which means availability, access control, logging, and abuse resistance become major concerns. In the retirement state, the model is removed or replaced, and that sounds boring until you realize that old models can keep leaking data, keep making decisions, or keep being reachable if decommissioning is sloppy. Security lives in transitions, because transitions are when assumptions change and controls can be bypassed. A beginner mistake is to treat model lifecycle as project management fluff, when it is actually a risk map that tells you where the most likely failures will occur. Training is the first state, and it is where the model's future behavior is largely determined, even if it will later be adjusted. Training means taking a dataset and an objective and learning a set of internal parameters that connect inputs to outputs. For security, training is also the moment when you decide what the model is allowed to learn from, which is a confidentiality and integrity question, not just a technical one. If training data includes secrets, personal data, or internal documents, you must assume those elements can influence outputs later or be recoverable in some form, which creates leakage risk. If training data can be manipulated by an attacker, you must assume the attacker can shape the model's behavior, which creates a quiet, long-term compromise rather than a loud, immediate one. Another beginner misunderstanding is thinking that training is simply feeding data into a black box, when in reality training includes data collection, cleaning, labeling, and selection, and each of those steps can introduce bias or errors. A defender thinks about training as a supply chain. You secure the inputs, you validate the process, and you document what went into the result. In the training state, the most basic security question is who can influence the training dataset, because influence is power. If a model is trained on security logs, for example, an attacker might try to generate activity that pollutes the dataset and nudges the model toward treating malicious patterns as normal. Even without malicious intent, messy or inconsistent data can teach the model the wrong associations, which later becomes a detection gap. This is why training often needs data governance practices such as access control, integrity checks, and clear lineage that shows where data came from and how it was modified. You can think of lineage like a chain of custody, the same way you would treat evidence in an investigation. Another issue is that training systems often require significant compute and privileged access to datasets, which makes the training environment a high-value target. If an attacker gains access there, they can steal training data, steal the trained model, or change training parameters to create subtle failures. When a scenario question asks what control matters most during training, the safe answers usually emphasize protecting data, protecting the training pipeline, and validating the dataset before trusting any performance results. Evaluation belongs tightly to training, because training without honest evaluation is just wishful thinking. A model can appear to perform well if you test it on the same data it learned from, but that success can be an illusion caused by memorization or leakage. Defenders care about honest evaluation because they care about how the model will behave on future data, including adversarial data, not just clean lab examples. This is why holdout data, careful splitting, and time-aware testing matter, because they reduce the chance of flattering results that collapse later. A beginner can misunderstand evaluation as a single score that proves quality, but quality is multidimensional in security. You care about false alarms, missed detections, stability over time, and how performance changes across different systems or user groups. Evaluation also needs to reflect operational cost, because a model that is technically accurate but operationally noisy can be worse than no model at all. If you internalize that evaluation is part of the training state, you stop treating training as complete when the loss curve looks good and start treating it as complete only when the model behaves reliably under realistic conditions. Tuning is the next state, and it is where many teams unintentionally create risk while chasing better numbers. Tuning means adjusting something about the model or its configuration to improve performance, which could include changing thresholds, selecting features, adjusting regularization, or performing a second round of training with new settings. The key security idea is that tuning is a change, and changes require control because changes can introduce regressions. A model that improves overall metrics might quietly worsen performance on rare but high-impact attacks, and that can be a catastrophic trade in a security context. Tuning can also increase sensitivity to prompt phrasing or input variation in generative systems, which can expand the abuse surface. Beginners sometimes assume tuning is a harmless polished step, but defenders treat tuning like a release. You test, you validate, and you document what changed. You also maintain rollback capability, because when you change a model, you want the ability to revert if behavior becomes unsafe. In exam scenarios, tuning is often where the correct answer involves revalidating rather than trusting improvements based on a single metric. The tuning state is also where you see the tension between performance and predictability. As you tune, you may push a model toward being more aggressive to catch more threats, which can increase false positives and create alert fatigue. Or you may tune it to reduce noise, which can increase false negatives and create blind spots. Defenders translate those trade-offs into risk decisions that must align with the organization's tolerance for disruption versus missed detections. Another subtle risk is that repeated tuning can lead to overfitting to a validation dataset, especially if the same validation set is used as the target over and over. When that happens, the model becomes good at a test rather than good at reality, which is exactly what attackers hope for. Tuning also creates governance questions about who is allowed to change the model and how those changes are reviewed. A model that can be tuned by many people without oversight becomes a soft target, because an attacker only needs one weak link in the process. If a scenario describes a model whose behavior changes unpredictably after frequent adjustments, a defender's answer is often to tighten change control and require consistent, repeatable validation gates. Serving is the state where the model is operating in the real world, receiving real inputs, and producing outputs that influence decisions. This is where classic security concerns return strongly, like authentication, authorization, rate limiting, and logging. But with a twist, the inputs themselves can be adversarial and the outputs can create new kinds of harm. In serving, the model's interface becomes an attack surface, and that interface might be a user prompt, an event stream, or an internal service call. Serving also introduces availability risk, because if an organization depends on a model to triage alerts or guide workflows, an outage or a denial of service attack can degrade security operations. Another serving risk is confidentiality, because the model may be given access to sensitive context, like logs or internal knowledge, to produce better answers. If that context is too broad, a user can cause the system to reveal information it should not reveal, even without meaning to. Beginners sometimes think serving is simply running the model, but defenders see serving as deployment plus operations plus adversarial pressure, which means controls must be layered and monitored continuously. Monitoring is the heart of safe serving, because serving is where reality will challenge every assumption made during training and tuning. Models can drift when user behavior changes, when system configurations change, when new applications appear, or when attackers adapt their methods. Drift is dangerous because it often looks like ordinary noise until the model is already unreliable. A defender's approach is to watch both input characteristics and output behavior over time, looking for changes in alert rates, confidence distributions, and error patterns that suggest performance is degrading. Monitoring also includes feedback loops, where investigations confirm whether alerts were correct, because without feedback you cannot measure real-world precision and recall in a meaningful way. Another serving concern is how the model is used, because misuse can turn a helpful tool into a risky one. If the model's output is treated as authoritative without verification, errors can propagate quickly into decisions, especially if the output is persuasive. In exam terms, when you see a scenario about a model being deployed successfully and then later becoming less reliable, drift awareness and ongoing validation are usually the correct conceptual anchors. Serving also forces you to think about boundaries, what the model is allowed to access, what it is allowed to do, and who is allowed to ask it for help. In systems that connect a model to other services, there is a temptation to give the model broad access so it can be more useful, but broad access increases blast radius if something goes wrong. A core security principle is least privilege, and it applies just as strongly here, because model outputs can be manipulated through inputs. Even a well-intentioned user can accidentally include sensitive data in a prompt or request a summary that exposes confidential details. Attackers can be more direct, trying to coerce the model into revealing internal information or triggering unsafe actions. This is why permissions, scope boundaries, and strong auditing are so important in serving. It is also why defenders care about separating data context by user role and ensuring that the model's context is aligned with what the user should legitimately see. If a question asks what to prioritize when deploying a model into production, answers that emphasize access control, monitoring, and controlled context exposure align strongly with defensive thinking. Now we reach retirement, which sounds like the quiet end of the story, but is actually a security-critical stage. Retirement means deciding that a model should no longer be used, either because it has been replaced, because it has drifted too far, because its training data is no longer appropriate, or because it no longer meets governance requirements. Retirement criteria are the rules that tell you when to stop trusting the model, and those rules are part of responsible lifecycle management. A beginner misunderstanding is assuming a model can simply be left in place while a new model is introduced, but that creates risk because old models can remain reachable, remain integrated into workflows, or remain embedded in automation. Old models can also represent outdated assumptions, like older threat patterns, older policies, or older data handling expectations. Another retirement issue is that models can carry sensitive information in their learned parameters or in their configuration, which means retiring a model includes deciding how to store it, who can access it, and whether it must be destroyed or archived under strict control. In exam scenarios, retirement is often the overlooked answer, but it becomes correct when the safest path is to remove a risky system rather than keep patching it. Retirement criteria should be specific enough that they can be acted on without emotional debate. One criterion might be sustained performance degradation that cannot be corrected with safe tuning, especially when that degradation creates unacceptable false negatives or false positives. Another might be a governance change, such as new privacy requirements that make the original training data unacceptable. Another might be a security incident, such as evidence that the model or its pipeline was compromised, which makes the integrity of the model's behavior untrustworthy. Retirement can also be triggered by operational factors, such as a model becoming too expensive to run or too unstable to support. The important security idea is that retirement is not a failure. It is a control because it prevents continued exposure to known risk. Defenders retire systems all the time, like deprecated protocols and unsupported software, because keeping them is worse than replacing them. If you treat retirement as part of the normal life cycle rather than as an embarrassment, You make safer decisions, and you reduce the chance of lingering, forgotten attack surfaces. A responsible lifecycle also includes clear handoffs between states, because many real failures happen in the gaps. Moving from training to tuning should include documented baselines, evaluation results, and clear definitions of what success means. Moving from tuning to serving should include deployment readiness checks, access control design, monitoring plans, and rollback plans. Moving from serving to retirement should include a clear plan for decommissioning, archiving, or destruction, and communication to stakeholders so the model does not quietly remain in use somewhere. Beginners sometimes imagine that lifecycle states are neat boxes, but in reality they overlap, and that overlap is where confusion and unsafe shortcuts appear. This is why defenders like change control, documentation, and approvals. They reduce ambiguity and enforce intentional transitions. In scenario questions, the best answer is often the one that acknowledges the transition risk and recommends adding validation gates, monitoring, or formal criteria rather than relying on informal confidence. Lifecycle thinking turns scattered controls into a coherent safety system. One of the most useful beginner shifts is realizing that a model's lifecycle is also a data lifecycle. Training data needs governance. Tuning data needs careful handling. Serving data needs access controls and retention decisions. And retirement includes deciding what data traces remain. Data retention can be a security risk if sensitive prompts, logs, or context documents are stored longer than necessary or accessible to the wrong people. Data can also create compliance exposure, because models that interact with user information can fall under privacy expectations that require controlled use and deletion. Another subtlety is that labels and feedback gathered during serving can become future training data, which means serving can influence the next training state. That feedback loop is powerful, but it also means that poisoning, mislabeling, or process changes can shape future models if governance is weak. A defender sees the feedback loop as both an improvement mechanism and an attack path, which is why integrity and provenance matter beyond the initial build. If you connect lifecycle states to data flows, you will naturally choose safer answers on questions about leakage, drift, and operational control. The deepest takeaway is that lifecycle states are not just descriptive. They are decision points where you choose what you are willing to risk and how you will notice when you are wrong. Training decisions shape what the model can learn and what it can leak. Tuning decisions shape how it trades false alarms for missed detections and how stable it remains under change. Serving decisions shape the attack surface, the monitoring posture, and the operational impact of mistakes. Retirement decisions shape whether old risk lingers quietly and whether sensitive artifacts remain exposed. When you learn to name these states and their typical hazards, scenario questions become less intimidating because you can ask a simple question: what state are we in, and what is the most important control or criteria in that state? That question is a defender's compass, and it points you toward answers that prioritize validation, least privilege, monitoring, and clean decommissioning rather than hope and optimism. If you can explain the life cycle clearly and connect it to risk, you are thinking the way security AI plus wants you to think, and you are building a mental habit that stays valuable long after the exam.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.